Hello everyone, I'm Peter Hurley, one of the project scientists on the Herschel Extragalactic Legacy Project. During this talk, I'll give a brief introduction to how we're using probabilistic programming to explore some of the rare and interesting objects observed by Herschel. So as many of you will be aware, the Herschel Space Observatory's been transformative for far-infrared astronomy. In particular, it's been key for understanding extragalactic star formation. And that's because half of the starlight emitted by stars within galaxies is absorbed by dust and re-radiated at infrared wavelengths. Also, as you go to higher redshifts, that dust peak shifts towards longer wavelengths, enabling Herschel to detect some of those high redshift star-forming galaxies. Now, Herschel observed numerous extragalactic survey fields at a mixture of depths. For example, the deep cosmos field to shallow but wide Herschel Stripe 82. Now, the objective of the Herschel Extragalactic Legacy project has been to provide all of this Herschel survey data alongside ancillary data products, such as photometric redshifts and spectral energy distribution fits to the wider community. And today we've got our first public data release alongside the main project paper you can find in archive. And although ground-based facilities such as Scuba 2 and ALMA can observe in the far infrared and submillimeter, they don't cover the same extent of area as Herschel. There's also no planned successor to Herschel. So in terms of having a far infrared data set that covers the sort of area you need to get a statistical handle on rare objects, which challenge galaxy formation scenarios, we're going to have to rely on Herschel for the foreseeable future. That said, Herschel data is challenging to work with, mainly due to the issue of source confusion. Now, the Herschel spiral maps have relatively poor resolution compared to the optical. Therefore, we've got a challenge of working out which galaxies observed in the optical and near infrared that the far infrared flux is associated with, or whether that flux is coming from multiple sources. Now, there are two traditional ways of assigning flux in Herschel maps. You can use a blind source detection approach, where you detect all the bright sources, but you then have the challenge of assigning those sources to galaxies from other observations. The prior-driven approach takes a list or catalogue of galaxies observed at other wavelengths and use that to distribute the flux, with the disadvantage that you'll miss the unknown sources. The key point to remember is that whatever approach you take is part of your data model. If your data model isn't appropriate, you can get the wrong interpretations. Now, the blind source detection approach has been very fruitful for Herschel. For example, it's been used to detect high redshift starbursts, such as HFLS3. Many of the bright objects have been found to be lensed galaxies, as confirmed through follow-up on ALMA. And some of those bright source objects are thought to be galaxies undergoing extreme star formation on the order of 20 to 30k solar masses per year. Now, given the limitations of that blind source approach, we have been looking at whether the interpretation changes if you take a more prior-based approach to distributing that flux on the Herschel maps, and how machine learning can help. Now, one way to think of machine learning is to split up methods which are discriminative or generative. Discriminative methods, such as neural networks or SVMs, offer problems where your main objective is prediction. They're great if you've got big data, and they can capture any intricate structure you might not be aware of. However, it has a disadvantage that it can be difficult to impart any domain knowledge you have on the problem. It can be difficult to understand or interpret why your model's made the decisions it's made, and many of these methods lack a principled estimate of uncertainty. Generative methods, on the other hand, can provide a principled estimate of uncertainty and allows you to input your any domain knowledge you have on the problem. However, for certain problems you might not have enough domain knowledge to make the assumptions you need to make for these methods to work. Many of these methods are challenging to fit and often become intractable as you move to large data sets. Another way to think of generative models is to think of them as invertible simulators. We can write complex simulators in astronomy, for example, the dark matter simulations or radiative transfer models. Simulations run one way. They go from parameters to data. What we want to do is run them in the reverse, go from data to parameters. And that's what probabilistic programming is allowing us to do. We can define our generative models which can run both ways. Up to fairly recently, inference on those generative models has been challenging. It's required writing inference algorithms for each particular problem. This is where probabilistic programming is changing things. It's abstracting out that complexity, allowing us to focus on building models for science. And this has been feasible because recent developments in algorithms, such as the no U-turn Hamiltonian Monte Carlo sampler and variational inference, have been packaged into user-friendly software such as Stan, PyMC3, and Pyro or NumPyro. So I'm using this approach because I have domain expertise on the problem. We are using a prior-based approach to assign the flux from catalogues we have from other wavelengths. We have photometric redshifts. We have some understanding of the spectral energy distributions of galaxies. We've got some idea of statistical relations, such as luminosity functions. More importantly, the issue of source confusion results in degeneracies, which makes the usual approach of first constructing catalogues, then doing SED fitting, followed by fitting statistical models, a lossy one. If possible, it's better to try and do it all simultaneously. So we've been using this probabilistic approach within HELP and developed XLE Plus as a probabilistic deblender. For that first data release, we've just been using position information as priors, as you can see by the black variables in our probabilistic graphical model here. We've been taking that steps further now by incorporating SED modeling via emulators, using that helped photometric redshifts as additional prior information, and beginning to impart more domain knowledge. For example, to first order, that star formation rate linearly increases with redshift, with some sort of dispersion. Now, incorporating SED models isn't straightforward, they're fairly complex. However, we can emulate our favorite SED code, either Segal or Magfizz, using neural networks. This isn't a new idea. It's been used to emulate the Grazel radiative transfer code in the past, and more recently, the stellar population synthesis models. What is novel is using them inside a probabilistic model. So we've been using this XLE plus SED framework to explore some of those extreme starburst candidates found from the blind catalogues. And to show you how this works, let's look at an example. So the three maps here are the three spire bands observed by Herschel of our extreme starburst candidate dead in the center. Now, we use two models. The first contains all the sources from the HELP master list with detections in 3 or more optical near-infrared bands, including the candidate. Our alternative model uses the same, but to mimic the assumption that the blind catalogues make, i.e. all that flux goes to that one candidate, we remove all sources that are within 18 arc seconds of that candidate starburst source. Because we're using a Bayesian inference approach of XLE+, we don't just get the best fit, we get all fits that are most probable. And we can use all those probable fits to construct a more robust residual map, which we call Bayesian p-value maps. And they provide a visual check to which model is appropriate. Where a model has too much flux compared to the data, you'll see as blue pixels. If there's not enough flux in the model, you'll see that as red pixels. On the top row, you see our first model, second row, the alternate model. And as you can see, that alternate model is struggling to fit the map, and there is an additional galaxy there we need to include to get a better fit, i.e. that extreme starburst source cannot be explained by one galaxy. Now we can use our model, our preferred model, i.e. all the sources, and look at the inferred physical parameters such as star formation rate and redshift. Here's the joint posterior distribution in blue, prior distribution in red. Black lines are showing what were suggested as star formation rates and redshifts from previous investigations. And as you can see, our model suggests this source is not undergoing extreme star formation. More interestingly, we've got that hierarchical relation between star formation rate and redshift, which we are also fitting. And you can see in the plots here how that looks, including on the right with the redshift star formation rate plane, where our galaxies have been fitted in black. Now we've been fitting this to individual galaxies. The next step, and more exciting, is to take this to fitting larger regions and moving beyond linear relationships to more principled parameterizations, such as the Schechter functions. And I'll leave you with my conclusion slides. Thank you very much.